This is the DBF at Virginia Tech video submission for the 2020-2021 competition cycle. We are proud to present our aircraft, Xiphius.
Design Build Fly at Virginia Tech is composed of 33 students, consisting of 2 seniors, 4 juniors, and 8 sophomores in various leadership positions, as well as 20 sub-team members. We are very grateful for this team and the opportunity given to us by DBF and AIAA.
This is an overall view of the Virginia Tech DBF competition aircraft, Xiphius. Some important things to note include the wingtip fences, which were sized to improve aerodynamic qualities. The wing has an FX63-120 airfoil, which boasts an impressive lift-to-drag ratio. The fuselage is made of carbon fiber to be lightweight and carry 28 shipping container simulators. The triple tail effectively balances the moment of the wing as well as provides lateral directional stability. The sensor has 3 sets of fins to help stabilize during deployment and flight. The sensor is 5 feet long and deploys 50 feet below the plane before 3 LEDs are turned on in pattern. The landing gear is sized to minimize the shocks of landing, and the high-speed propulsion system enables Xiphius to take off within the 100-foot limit and cruise over 100 feet per second.
A score sensitivity analysis was developed to determine which scoring factor had the greatest effect on the overall competition score. The left chart shows that the report is the most important part of the competition, with missions 2 and 3 having a similar effect on the overall score. In mission 2, increasing the number of simulators in the aircraft improves the score at a linear rate, while decreasing the mission time improves the score at a non-linear increasing rate. The pattern seen in mission 2 holds for mission 3, where the sensor length and weight have linear score returns on improvement, while the number of laps and consequently the time per lap has a non-linear increasing rate of return. This CAD-generated 3-view shows the sizing of the aircraft. This aircraft is consistent throughout each mission. Xiphius has a span of 60 inches and a tip-to-tail length of 77.3 inches. This is a 3-view of our completed competition build.
All control surfaces are controlled using a Futaba receiver, which in turn transmits signals and 6 volts to all servos. All control surfaces are actuated by Emax servos, which have a stalled torque of 27.77 ounce-inch, which is adequate to counteract all hinge moments.
The Hacker A60-6XS motor was chosen as the motor for all missions. For mission 2, a 6S2P 4500 mAh battery was chosen with a 20 by 13 inch prop to provide 15.9 pounds of static thrust, allowing it to achieve a top speed of 104 feet per second. For mission 3, a 5S2P 5000 mAh battery was chosen with an 18 by 12 inch prop, which gives 11.1 pounds of static thrust and results in a top speed of 83.9 feet per second.
The wing was sized to provide adequate lift during takeoff while minimizing drag during cruise. An FX63-120 was chosen with a combination of a 12-inch root cord, an 8-inch tip cord, and a 60-inch wingspan. 70% of the wing is dedicated to flaps, covering 20% of the cord, with a maximum deflection of 40 degrees. Ailerons were sized to span 16.7% of the wing and 30% of the cord, with a maximum deflection of 10 degrees.
The tail was sized to counteract the moment caused by the wing. To do so, the horizontal tail was chosen to consist of an inverted NACA 4412 airfoil with a span of 24 inches and a chord of 4.5 inches. All verticals are a NACA 0012 airfoil. The center vertical has a span of 6 inches and a chord of 4.5 inches, while the outer verticals have a span of 6 inches and a chord of 6.5 inches. The elevators consist of 20% of the chord and 100% of the span with a 20-degree max deflection. All rudders are 100% of the span with a 30-degree max deflection. The center rudder makes up 30% of the chord, and the outers consist of 20.8% of the chord. This configuration gives a static margin of 12%.
The gross weight for mission 2 will be 25 pounds. Full flap deflection will allow for a takeoff of 75 feet. The rate of climb up to cruise altitude is 41.8 feet per second. The stall speed is 53.7 feet per second, and the turn radius is 192.5 feet for each turn and loop. The gross weight for mission 3 is 12 pounds and will allow for a 50-foot takeoff. The rate of climb is 30.3 feet per second. The stall speed is 38.9 feet per second, and the turn radius is 116.9 feet.
Thank you for a wonderful competition year. Let's go!
Hokies!
And opening doors. Deploying. Stopping. LEDs on. LEDs off. Retrieving. Bomb bay close. Mission complete.
In regards to takeoff and landing, Xiphias can take off in 75 feet, meeting the 100-foot requirement. The tail dragger landing gear is sized to absorb the shock of the landing gear and keep the aircraft straight as it lands on the runway. For the sensor design, the team created a 5-foot sensor made out of carbon fiber with 3 LEDs. The deployment system is controlled by an Arduino Uno that communicates with the receiver. The sensor is controlled by an Arduino Nano that communicates through a 50-foot ground and 50-foot signal wire that runs up into the aircraft into the Arduino Uno. Before deploying, a bay door is opened to reveal the sensor. The speed of the deployment can be controlled using assigned knobs on the transmitter.
Begin sensor deploy.
Opening doors. Deploying sensor.
I'm going to begin a big circle.
You can see it coming down.
Big circle time. Oh, looks good. Look at that. That's fantastic.
You're doing great.
This is awesome. Nice.
Can I reel in?
Yep.
I'm going to reel in.
I'm just going to keep it straight for a minute. Turn to the left. You got 3 minutes. Is it coming in?
Yeah.
Fantastic.
It's slow at first because that's what's right.
Similarly to the deployment system, the retrieval system reverses its process, switching the knob's direction to bring in the sensor until the sensor is fully retracted and the bay doors close.